Hi everyone. In this video, we will discuss the problem possible paths in a tree. The problem says that we'll be given a weighted tree. So basically, we'll be given a tree in which every path will be weighted. And there are n nodes inside this tree and total n minus 1 edges are there. Because if a tree has n nodes, then the number of edges will be n minus 1 as we all know. Now we'll be given q queries inside this tree, and for each query we'll be given a particular value, that is x. And for each of these queries, we have to find the number of paths in which the maximum edge weight is less than or equal to x. So we have to note that the path from A to B and B to A are considered the same. Suppose that we have got three nodes. So let's say we have got n value as 3. Now if the n value is 3 and we have been given the triplets of the edge, so suppose we have been given 1 comma 2 comma 1 and another triplet we have been given as 2 comma 3 comma 4, right? So in this case what will happen is you can say that 1 is connected with 2 and the edge weight is how much? The edge weight would be 1. And then you can say 2 is connected with 3 and the edge weight for this would be 4. Okay, because firstly we are given what? We are given the starting, ending and the weight. So we are given the node A comma B, and then we are also given the weight of it, right? After this, if you will see that like in the first query there is only one query for this first test case, and we have been given the query as 3. So we have been given the query as 3. So basically we have to find that how many paths are there inside this particular tree such that the maximum edge weight is less than equal to x, right? So you can understand that in this query you have been given the x value as 3. So how many edges are there that have the weight less than equal to 3? Only one edge is there, that is between 1 to 2. Okay, so only one edge is there. So that is why the answer for this test case would be 1. You can see. So the path between 1 to 2, which is having the weight as 1, would be considered. Now after that, if you will see the next test case, so n value is 7 and the edge list have been given. So basically in edges you have been given a, b and the weight. So suppose that n value is 7 here, and we have been given what? We have been given the triplets as 1 comma 2 comma 3, and then after that we have been given what? We have been given 2 comma 3 comma 1. Then after that we have been given 2 comma 4 comma 9. Then after this we have been given what? We have been given 3 comma 6 comma 7. Okay, and then after this we have been given 3 comma 5 comma 8, and then lastly we are given what? Lastly we are given 5 comma 7 comma 4. So if we are given all these nodes, then you can basically see that 1 is there, so you will connect 1 and 2 together, right? And the weight will be 3. Then after that you will say that 2 and 3 needs to be connected, and the weight between them will be 1. After this you will connect 2 with 4. So 2 is connecting with 4 and the weight of this edge would be nothing but 9 here. Then after this you will connect what? You are going to connect 3 and 6. So let us quickly connect 3 and 6 here. So 3 will be connected with 6 and the weight for it would be 7. Then after this we'll connect what? We'll connect 3 and 5, and then the weight will be what? The weight will be 8 here. Then after this we'll connect what? We'll connect 5 and 7. So 5 is there, so we'll connect it with 7 here, and the weight will be nothing but 4 here. Notice that we have to understand one thing, that in this case the triplets that we have been given, we are only able to form one tree, but there can be more than one components also, because if suppose that you're given the connections in such a way that you can make more than this. Okay, so basically if you will see here, what you need to do is, once this has been given, so let's see the first query. The first query is having the value as 1. So in this query, if you are having the value as 1, so you have to tell that how many edges are there that have the weight less than equal to 1. So there is only one edge like this, so you will answer it as 1. Then after that, how many edges are there that have the value less than equal to 3? So basically 3 edges are there, because the edge the path from 1 to 2, 1 to 3 and 2 to 3 will be considered. So 1 to 2, then 2 to 3, and then 1 to 2, 2 to 3 and 1 to 3 will be considered, because you have to consider the paths. So these will be the paths. Okay, so the path from 1 to 2, 1 to 3 and 2 to 3. So let's see, 1 to this and then this and then this. Okay, so then the answer would be 3. And for the last case, when you have the query as 5, so how many paths are there? So path between 1 and 2 will satisfy, 1 and 3, 2 and 3 will satisfy, and 5 and 7 also will satisfy. You can see the path between 5 and 7 is of 4 weight, which is less than equal to 5. So what we have to do in this particular problem is, if we want to solve this problem, So first of all, when we are connecting, right, when we are connecting the edges, so obviously we have been given A and we have been given V, and then whenever we connect A and B, so the weight between them is W. So what we can do first of all is we can make a pair of the weight and A comma B. So basically, suppose that there is a node A, there is a first node and second node A and B, and in between them the weight is W. So I will make a pair in which I'll have the first part as the weight and the second part will be pair A comma B. And then what we will do is we can basically make all these pairs and then we can sort them. How we can sort them? In the ascending order. Now once we have sorted them, then we will try to connect all those weights one by one. And while we will try to connect, so which data structure can easily help us to connect a node A and B? So basically we can use the DSU, disjoint set union, or union find in order to do this. Why? Because disjoint set union will allow us to connect two nodes A comma B with the weight as W overall for all the parts in order of n time in the worst case. So that is why it will help us to linearly connect the edges, and that's how we can build the component. And once we have done that, then we can easily find our result. So let us quickly start writing a little bit of code so that we can understand how we'll implement this. So firstly, what we'll be doing here is we will first of all declare two arrays, because since we will be having what? Since we'll be having the DSU, so we need the parent array as well as the size array. So in this question, I'm assuming that you already have the prerequisite field, that is, you already know about disjoint set union data structure. So what you will do here is, first of all, you will be iterating in this particular given scenario. So firstly, what we are going to do is we are going to declare a parent array. So let's say we will first of all do what? First of all, let's mark our answer as 0. We'll declare our answer variable, and then for every test case that we have, like, we'll mark our answer initially as 0. Then after this, what we are going to do is we are going to declare a parent array of n plus 1 size. Let's name it as parent, and then initially let's say we will declare it and then mark it as 0. Then after that, we also need to declare a size array. Let's say vector int size. Size will represent the size of the components, and here what we are going to do is we are again going to declare the size as n plus 1. Initially we'll initialize everything as 0. Then after this, what we will do is we'll iterate through all the nodes. So I starts from 0, I is less than equal to n, then I plus plus, and then what I will do is I'll say that initially every element is going to be its own parent. So I'll update the parent of I as I only, and also one more thing, what we are going to do is we are going to update the size as what? Size of the ith node will be made as 1. So initially we are going to declare all the sizes as 1. Now once we have declared the parent array and the sizes, then we need to make a pair in which we want to store what? First of all, we want to store the weight, and in the second part of the pair we want to store a pair again of A comma B. So we will declare a vector of pair, then pair int comma int, let's name it as V, and then after this, what we will do is we'll iterate through all the edges that are given to us. Okay, so let's say that we'll while we are iterating, so we will be doing what? I starts from 0, I is less than edges dot size, right? And then we can simply do y plus plus. So we'll be iterating, and then let's say A will be what? A will be nothing but edges of I 0. Then what will be B? So you can say that B will be nothing but edges of I then 1. Okay, then C will be what, guys? C will be nothing but edges of I 2. Okay, now once we have the edges, then what we are going to do is we are going to push back nothing but uh, let's name this as W. So yeah, what we are going to do is we are going to push the weight, and then we are going to push the A comma B. Okay, now once we have done this, so after we have stored all the pairs, like all the triplets, you can say indirectly, then what we will do is we will sort our array. So we'll sort it according to the ascending order of the weight. So in C++, when we will write sort function, so it always sorts according to the first parameter. That is why we have taken the first parameter as weight. So it will sort according to the ascending order of the weight. Now once we have sorted according to the weight, then we can declare a map. Now what will map allow us to do? Map will allow us to store the weight of the component, maximum weight of the components, right, which will be used later on. So what we will do is we'll declare a map. Why we are declaring a ordered map? So that the keys are there in sorted order in this particular map. Now when we have this map, so again what we will do is we'll iterate, and we'll iterate through all the edges again. So I starts from 0, I is less than n, I plus plus, and then what we will do here is like I is less than edges dot size, let's say. Okay, and then we'll do I plus plus. Now while we are iterating, so again I will copy a, b and w, because a, b and w are going to be the same here. So when we are iterating, so we will check. What we will do is we are going to do the union. So if I wanted, I could have done it like this, or let's say if I wanted to write the weight, so I can write the weight as what, I can iterate through all the edges. So let's say what we can do here is we can run till less than v dot size. Okay, and then what we can do is w is equal to v of I dot v of I dot first, because in the first part we'll be storing the weight, and then int a will be equal to what, a will be nothing but v of I dot second dot first, because in the second part first we are storing the a. Then b will be what, guys, it will be nothing but v of I dot second dot second. Okay, once we have stored this particular thing, then after that we will call the union function. So what we are going to do is we will try and do what, we will try and do the union of the nodes, let's say a comma b, where the like we'll try to do the union of these two nodes, and we'll pass the parent along with the size array as well, because we'll be doing union by size here. Now what will this function return? So it will help us to update the map, right? So this particular thing is going to this particular union function, it will help us to update the map with the maximum weight of the connected component after every union operation. So basically it will update the map, like, so we can write w mp of w, so it will update the map with the maximum weight of the connected component after every operation. Now after this function will be over, so we'll complete the union and the find parent function also. So then we need to return the final results for every query. So what we will require is, we'll require a list which will be storing all the results. So what we will do is we'll iterate from I starts from 0 till I is lesser than q, and then I plus plus, and then we will access all the queries. So let's say the current query will be what, let's say if I'll mark it as double q, then it will be nothing but queries of I. Now while I'm inside the map, so what I want to do is I want to find the element. Okay, since I want to find this thing, so I'll try to find what inside the map. Since the map is in sorted order, so I can apply a upper bound on the map, and suppose if the map is containing certain elements, so what I will do is whatever is the current query that I have, right, whatever is the current x that I have, I will try to search inside the map. So inside the map we will try to search from the beginning. Okay, we will we will basically apply the upper bound, and we'll try to find the index of the first element that is having value greater than x. Okay, once we find that, so how will that help? Because inside the map, if we have stored our results, okay, suppose inside the map we are storing the results, so suppose that map is having the values in the ascending order. Now if we had a x value, right, so we'll find the index of the first element that is greater than x. Once you find that particular value, then what you will do is, if you will do value minus minus, then your value variable, let's say, will come here, and that will basically indicate what, that particular value variable at that point inside the map, it will indicate the all the weights that are less than like if you have this map, then if you will apply upper bound, so it will point to the weight which is just greater than x. Then after that, when we do value minus minus, then it will point one step backwards, and then after that we can return v dot second, because we have to return the, basically we have to store the maximum weight for every query, right? So what we will do here is we can simply say here that once we have got this, then we will check that if the value that we are getting, if the index that we are getting, map dot upper bound, so let's write this upper underscore bound. Okay, so if the value or the index, you can say, is equal to map dot end. So if it is equal to map dot end, this means that, or let, instead of value, let's write this as idx. Okay, so let's write this as idx. So if the index is equal to the end of the map, so this means that there does not exist any, because if we were searching for the value inside the map that is just greater than the given weight x, then in that case, if it is not existing, then you will go outside the map, so index will be equal to the map dot end. So if that is so, then in this particular case we will say that there is no such path, and we need to store what, we need to store inside our result 0. Okay, So we'll do result dot push back 0. So simply we are going to push 0. Else what we will do here is we will simply do what? We will say that we need to decrease the index. Okay, because we are pointing currently at the index which is having the weight greater than the given x. So we want to find for the lesser. So we'll move one step backwards, and once we have done that, then we will store this particular result. So we'll do what? Result dot pushback, and then we will do uh, index second. So basically at this index, whatever second value has been stored, it will tell us about the total number of edges that have the weight less than equal to the given value x. Okay, so this is how we'll be able to store it. And obviously we'll apply certain changes in the union function in order to do it, because union function not only will do the union, but it will also store the total number of pairs as well, right? So like in this case, you will do what? At the end, you will just return the result. So now let's try and implement our parent function. So like find function. So since we have to find the parent, so what you can do is, let's say we can write a root function. It will help us to find the ultimate root of that component. So suppose that if I am currently at a particular value and I have also got my parent array, so vector int ampersand parent array is what we have got, then what we can do here is, like, we can say that while the parent of the current node is not equal to the current node itself. So this means that if it is not the ultimate parent, then we can say that we can keep on updating. So we'll say that the parent of I will be nothing but it will be equal to parents of parent I, right? So we will call for our parent's parent, and whatever result it returns, we will store it. And then after this, we'll say that current node will be equal to the parent of the ith node. So what we are doing here is we are trying to apply this in an iterative format where we are trying to find the ultimate parent for that particular connected component. Now once that is done, so we need to implement our union function. So what we will do here is we'll write int union, and now in this particular union function, the task for this union function is not only to perform the operation of the union of two sets, but also return the size of the resultant set. Okay, so what we will do here is when we are going to do the union, so let's say we'll have the node two nodes, let's say A and the B node. Okay, and then we will also be storing what? We'll be storing the parent here, right? And then we will also do what? We'll also be having the vector int and ampersand size here. Right, now what we will do here is we will simply check. So we'll find the ultimate root of the node A, okay, and then we'll find the ultimate root of the node B. So we'll name it as root B. Now after this, what we will do is, once we have found the ultimate roots, so we will check that if the ultimate root of A and the ultimate root of B are same. So this means that both of them are belonging to the same component. If the roots are belonging to the same component, so this means that they are in the same set. So in that case, we will return the size of the current set. That will be nothing but the size of RA into RB. Okay, sorry, size of RA into RA only we can do, because RA and RB are same. Otherwise, if it happens that they are different, then in that case, if they belong to different components, then we'll check if the size of the first component is less than the size of the second component. Okay, because we are checking the size of the ultimate parent. Then if the size of the first component is lesser, so I'll always assume that the size of the first component is bigger. Then in that case, what I will try to say is that I will swap the RA with the RB. This we are doing so that we can maintain a uniformity. So we will swap A and B as well. Okay, because we'll always try to think that the component which is having the node A is the larger component. Okay, if that is not so, then we'll reverse the nodes. Now after this, what we will do is we'll say that inside our answer, we can update the answer with nothing but the size of the uh, node RA into RB, because it will be nothing but the product of the size of the resultant size will be nothing but the product. It will be the product of the size of the two sets, right? Now after that is done, then we need to say that the parent will be updated. So parent of RB will be, let's say I can update the parent of RB as RA, because the smaller will join the bigger component. And once that is done, then we need to update the size of the bigger component with the size of the smaller one. Okay, now once this is done, so then we can directly return our answer, that is the size. Now I think I have implemented it correctly. Let's try and check the code if it is working fine on the samples or not. Okay, so it says that I was not declared. Yes, so since I had taken current in the root function, so I should write current here. Let's try and compile it again now. Okay, so it is giving us a compilation error now. It says that there is a colon that is missing somewhere. So let us check where we are missing the colon. And in the union function also there is some mistake. Okay, so yeah, when we are calling the root function here, then we should pass the parent array as well. So let's pass this parent array here, and let us pass this parent array here also. Okay, this was our mistake that we have been doing. So let us rectify it now. Okay, so yes, now the mistake is that there is one missing bracket at the end. Okay, and another mistake is that s was not declared, so sz is what we need to write in terms of size. Okay, let's try and run it again and check if it is working fine or not. Okay, so yes, another mistake is that we have declared pair, so v dot push back, v was not declared. Okay, so let us quickly check this. And then we are doing v dot push back. Let's open this here and let's open this here. All right, so I have now declared the pair as well, but there is some issue with it, so let's just try and fix it. So when we'll close this, then we'll close this and then this. Okay, let's try and again run it. So yeah, you can see it is working fine on the samples. Let us submit this code. And obviously the union find function was taking order of n, that is linear time. Okay, so there is some mistake because of which it is not able to pass all the test cases. Let us check the mistake. Okay, so I have my resultant declared here, and what I'm doing in my resultant is I'm always pushing back the index second. Okay, if it is equal to mapped. Okay, so yeah, since I'm finding the upper bound, so I should not do end, I should do begin. Okay, because if it is still pointing to the starting, so this means that there is no node. Now it is working fine on the samples. Let's try and submit. So yeah, this was one basic mistake that I did, because if I'm finding the upper bound, so I should do begin here. So if it is still pointing at the beginning, so this means that there is no element. Okay, if I'm finding for a particular element, which element is the first element that is greater than x, and it is pointing to the very first element of the map, so it indicates that there is no such pair, so that is why we'll return 0. So I hope that everyone is clear with this approach. In case if you have any doubts, you can mention in the comments. Thank you for watching this video.